Hi everyone, I'm Ollie Long and I'm here to talk about EMRI scattering by presenting the work I've done in collaboration with Leor. So first I'm going to talk about bound EMRIs and LISA. So an EMRI itself is a compact object orbiting a supermassive black hole. So these systems have small mass ratios less than about 10 to the minus 14. So these systems have complicated orbits as shown in the GIF, and there are around 10 to the 5 orbits that can be observed within a LISA band, which gives about a year of observation time. Now, the EMRI signals are weaker than the instrumentation noise, so in order to observe these, we need to use the large time within the LISA band, which can get a large cumulative signal to noise ratio. So now I'm going to move on to why we want scatter orbits. Well, it was shown recently that we can use self-force scatter data to get exact post-Minkowskian calculations for bound orbits. This means if we look at this plot, which shows the methods used in the two-body problem for separation against mass ratio, see we can use information from this plot on the bottom right to inform the weak field expansions at the top across all mass ratios. And this is also for bound orbits. If you look at the plot here, which is periastron against impact parameter, you can see that the scatter particles are highly penetrating, and even for relatively low energies, that the particle can dip well below the ISCO. This means that we can use self-force scatter orbits for calibration of effective one-body models in the ultra-strong field regime. Another thing we can do is compare with scatter amplitude calculations of scatter orbits within GR, such as those done with QFT or EFT methods. And obviously, these are very different methods used in classical general relativity calculations, so it would be good to contrast and compare. Another thing we can do is use a recently discovered dictionary between scatter and bound orbits. So we can use scatter orbits to inform bound waveform models, such as for LISA or LIGO. Now I'm going to move on to talk about scattering geodesics. So one parameterization we have is energy and angular momentum. And in this one, the energy must be greater than 1 and the angular momentum must be greater than a critical value. Otherwise, the particle will plunge into the big black hole. Similarly, we have another parameterization, which is velocity at infinity and impact parameter. Similarly, there is a critical value of B, whereas B is less than B crit, the particle will plunge. So the geodesics are described by a set of 3 ODEs in proper time tau. You can see these just depend on the constants of the energy and the angular momentum. This is also a good place to define what we mean by the scatter angle here, or you can see it graphically for this particular orbit here. So that was the geodesic case. What about when we add in self-force effects? Well, in self-force, we do expansions in the mass ratio. So here on the left, we have the full two-body metric of the system, and we expand this in this mass ratio eta. So the first term is just the Schwarzschild or Kerr metric of the big black hole, and then we add on these perturbations h order by order in eta. So restricting ourselves to first order, the equations of motion are given here. So the energy and angular momentum are now no longer constants. We have the geodesic terms as the 0th order, and then we have retarded integrals of the self-force. So these are the time and azimuthal parts of the self-force along the orbit of the particle. One thing we can do is split the self-force into conservative and dissipative pieces using the symmetry relation shown. And just to be clear, the dissipative self-force is the part which removes energy and angular momentum from the system. Now we're going to move on to look at the correction to the scatter angle. So we can write the scatter angle as a radial integral. You can see here that we have the integral from the periastron up to infinity, and this sum just means that we have to do it for the ingoing and outgoing orbits part of the orbit. So we can write this in this form on the right-hand side. You can see that here we have this root r minus rp, which will cause a divergence at the lower limit of the integral. So what we can do is substitute in the time-varying E and L and manipulate it, being careful to handle this divergent term at the lower limit. And this is complicated, so I'm not going to give details here. But the final result is we get something of this form as we expect. We have the 0th order geodesic and then the 1st order correction. which takes the form shown here. If we look at this, we have an integral from the periastron up to infinity, sum over both legs of the orbit. Then we have these functions g and gl, which are themselves functions of the geodesic parameters, and then the self-force components along the orbit. So again, we can split this into conservative and dissipative pieces, and we can write this as integrals on the outgoing leg only using the symmetry relations seen on the previous slide. And you can see when we do this, the equations have the general same form as the full equation. So now we have the equation that we want to use. We need to actually get the self-force to plug it in. So first to do this, we used a scalar field toy model, as it's much simpler than the full gravitational case. What we did was decompose the scalar field into these spherical harmonics, YLM, and then solve for these time radial fields, the lowercase psi. So to do this, we use a 1 + 1d wave equation. You can see here we have the principal part, and here these u and v's are just the advanced and retarded times on the light cone. You can also see we have a potential term and then the source term proportional to a delta function along the orbit of the particle. So we evolve this as a finite difference version of the equation above. The way we do this is we do it within a light cone and split in a uniform grid in u and v. We have initial conditions on the initial rays of u and v, and then solve the system iteratively through the grid, allowing the evolution to be sourced by the source of the wave equation along the world line. Once we do this, we need to get the scalar self-force. So in the scalar case, the equations of the motion have the same form as the gravitational case, except here the small parameter we expand in is proportional to this scalar charge q squared. So to get the self-force, what we first do is take derivatives of the scalar field along the world line, and then take the projection orthonormal to the fore velocity, and this gives us the scalar self-force F, which is what we need to put into the equation to calculate the correction to the scatter angle. So we did this for the orbit shown here on the right, and as you can see, for the azimuthal part of the self-force, there is a peak about periastron, which is at t = 0, but if you look closely, you can see the peak is actually slightly post-periastron. Now, if you look at the inset plot, which is the same data scaled by r³, you can see these undulations in the data. Now, we believe these to be quasi-normal mode excitations. Now, both of these effects have been seen in bound orbits, in highly eccentric bound orbits. So it makes sense that when we push the eccentricity further into unbound orbits, it's not a surprise that we see the same physical features. Next, we moved on to looking at the scatter angle, and we did this for a variety of scatter orbits. On the left here, you can see the orbits where we focused on the strong field regime, and on the right, you can see the orbits where we focused in the weak field. So these are the results we got. You can see on the main plots, we've plotted the blue dissipative piece and the orange conservative piece. You can see that when we're in the stronger field, that the blue dissipative piece is dominant over the conservative piece, but as we go further into the weak field, this actually swaps. If you look at the insets, you can see that actually the two pieces have different signs, which means when the conservative piece becomes dominant, that the scatter angle actually swaps from increasing the scatter angle to decreasing it, which is an interesting observation. Another thing you can see is that the full correction, this green line, is tending towards this red dash line. Now, this is a weak field 2pm expansion as calculated by Gralla and Lobo. And you can see that as we're going further into the weak field regime, that the results are getting closer and closer to this analytic weak field result, which is a good measure of showing that our results are consistent with what we expect. So for future work, what we want to do is calculate the gravitational self-force for hyperbolic orbits, which we can then use to get the gravitational self-force correction to the scatter angle. Once we have that, we can look at interfaces with other two-body GR modules, such as informing other models like PM and EOB, but also comparing with other models such as the weak field expansions, numerical relativity, or the high energy physics methods. Lastly, what we'd like to do is extend our model to a Kerr background or add in second order self-force effects. Thank you.